Hello, my name is Emmanuel Boutillon. I'm professor at the Université Bretagne in the laboratory LabStick. So today we'll present a presentation called Quasi Cyclic Short Packet for unslotted aloha transmission. It's work done through the Inria project QCSP with several of my colleagues, Kassem Saïd, Camille Molière, Christian Roland, Cédric Marchand, Leonardo Monteiro Bosso, and all the QCSP consortiums. So we have a paradigm shift in massive IoT. First, the classical cellular network is not adapted for massive MIMO because there is too much work, too much load for coordination. And then the solution is just to suppress coordination and accept collision. Second point, the classical modem of a frame is rather inefficient when the payload is small. In fact, if there is no coordination, then we need a header in order to make detection and to do synchronization. So classical frame is built by, it is based on a header, some data, and some redundancy. But if the payload of the header of the data is small compared to the header size, then a lot of resources will be wasted in the channel. So the solution is known, just to merge everything together, a joint header, data, and redundancy. So it will save bandwidth and will allow to have something more efficient. So the big bet of this project is to define new waveforms of IoT for very local sensors and in an unsupervised network. Okay, so let's go a little bit to see the stars. What we have is recently there were a modulation called cyclic code shift keying adopted by the Japan for their GPS enhancement systems from one side, and from the other side we have also non-binary error control code that has been normalized in the Beidou system, which is the Chinese GNSS systems. So QCSP approach is the joint modulation, CCSK modulation, and non-binary code association. Okay, so this is the outline of my talk. So first I will present the QCSP system model, then give some explanation on the receiver processing, give some results of the new radio implementation, multi-user detection, and then give conclusion and perspectives. Okay, so let's go toward system model. So first, what is a cyclic code shift keying modulation? It's quite simple. It's a spreading techniques. We have a sequence of size. Sorry, can I do that? Of size 8. So this is indicated here. And from this spreading sequence, I can generate 8 versions of the same sequence with a cyclic shift rotation. So for example, P0 is the original sequence. P1 is a sequence P0 with a shift of 1. So I put the first one in red in order to show that we have the same pattern, 11101, etc., 11101, etc., and so on. So we have 8 possible values so that we can encode 3 bits to select which one of the rotated sequence we're going to choose for the transmission. And when we select one, we use a BPSK modulation with a given roll of factors in order to have the waveform. So if I have a binary message, for example, 011001100, I will first split it in 3 bits. So first 3 bits, second 3 bits, and third 3 bits. So this one encode 3. 011 in base 2 gives me 3. This one encode 1, and this one 4. So in order to transmit this message, I will transmit the sequence P3, P1, and then P4. So P3 will be here. The one red one start at the 3 position, 0, 1, 2, 3. P1 at the first 0, 1 position, and P4, 0, 1, 2, 3, 4 position. So I can indicate it by the little cycle here that gives the initial position of my rotation. So this is a QCSP frame structures. So let's Q be the cardinality of the gateway field, which will be equal to 2 to the m. M is the number of the size of the MU plate. So my message will be k bits of k MU plate, and then I will use a non-binary encoder, so typically low density parity check non-binary encoder. Then I will generate n times m bits. So you have a code rate, an outer code rate of k over n. And then each m bit will be used by an inner code that will use to encode a sequence of likes q, which will be the CCSK sequence. I transmit through the channel. Then I will receive my message. And since the size code is very small, I can compute the probability of receiving of my observation, knowing that I've transmit each one of the possible code words, and then I will transmit QLLRs, log likelihood ratio, to the decoder, and then the decoder will suppress the errors up to the restoration of the initial message. So if it was my initial message, and I assume I have a rate one half, then I will generate 3 redundancy, for example, 7, 1, and 2 here. So this will be my wall frame. There is no header here, and I just have pieces of rotated sequences, 6 rotated sequences. I add also what we call another modulation at this point. That means we can multiply each symbol either by +1 or by -1 in order to add a known pattern of phase that is useful to help synchronization, but I'm not going to detail that too much. Okay, so if I look at now at the receiver side, I transmit the data in a channel, so I have a complex noise that is added. So I have a set of Q CCSK sequence. I select one of them, for example, P19, which is one of, I assume here that I have 64 sequence. I transmit it, I have some noise. So what I will receive will be the initial sequence plus some noise, and then my demodulation will just be the scalar product between what I've received and what I have expecting. So if I plot them in the complex point, one of them will have a high amplitude because it corresponds to the one that I have transmitted. And if I do the product scalar, I can see that I will have P19 multiplied by P19. So it will be P19 square. So since I make the summation on Q value, I will have a Q term that is constant. And then the other one will be a noise, will be some noise added. So if I look at the amplitude of my signal on the real part of my signal here, it's given here, and in 19 I will have a peak here that gives me what is the symbol that has been transmitted. Well, in real life it's a little bit more complex because there is a Doppler, there is some phase shift that can be due either to Doppler or local oscillators mismatch. And so what I have is that instead of having a real part that is important, I may have rotation. So here it's still okay, but if I have rotation of p over 2, then I will lose completely my information. And if I have rotation of -p, I will even not consider these symbols. So in order not to lose information, I have to take the absolute value. That means doing a non-current demodulation at the symbol level. And if I look at the absolute value, I will also have a peak here. Here I select P13. At position 13, I will also have a peak. And then we can show that mathematically the logarithm of the probability of receiving Y knowing that P has been transmitted somehow is linear function of this quantity. So just to give you some example of performance, this is a signal to noise ratio expressed as energy per symbol over N0. And this is the frame error rate, the probability that the frame is not correctly decoded. So we have here tests 3 different non-binary code, a polar code, a turbo code, and a LDPC code. And we can see that non-binary turbo code are better than LDPC and then than polar code. And what is interesting is that if we look at these curves here, this is a 5G rate 1/3 with repetitions that gives globally the same code rate. And we can see that from this point to this point, there is 1.5 dB of gain. So the payload here is quite small. It's 120 bits, and that shows that non-binary code with CCSK can overperform significantly the 5G code for small payloads. Let's take a look on the receiver algorithm. So in a glance, it's somehow I receive my message. There is some noise. There is time uncertainty. We don't know when the message will arrive, and we have frequency uncertainty. We don't know exactly which will be the frequency of the received message. So I call that a signal processing factory, where I'm going to use all the available redundancy of the inner code, of the overmodulation, and even of the outer code in order to be able to make a coherent demodulation. Then I will have my non-binary error control code decoder that gives me my decoded messages. So if I look at that, if I want to develop a blind detection self-synchronization algorithm, I have three problems. I need to detect the frame, the arrival of the frame in the noise. I need, if I detect it, then I need to have a correct synchronization, estimate correctly the exact time of arrival and the exact frequency and the exact phase. And then if I'm able to do that, I need also to be able to correct. So we can say that more or less the probability of correct detection will be something proportional to this product: correct detection, correct synchronization, and correct correction. So what we have to do to maximize the overall probability is maximize the minimum of these three values here, PD, PS, or PC. So it's a max-min problem. And what we did is to find all the parameters of the code rate, the overmodulation sequence, spreading sequence, in order to have all the three that are more or less equal. So for frame detection, how we do that? So this is a frame, BPSK frame, right? This is merged in the noise. This is a channel noise. So what we have will be at the receiver side, something like that. And in order to do the detection, we are going to do exactly like in the GPS systems. That means test in parallel different time and frequency hypotheses. And we'll have a match filter that accumulates maximum correlation on the length of the frame. And if it is above a threshold, then we said, okay, we have a detection. So it's somehow a trade-off between probability of false alarm, that's called here FA, and probability of misdetection. So we did a theoretical model that has been published in these papers that allow us to estimate for a given probability of false alarm, what is the probability of misdetection? So probability of false alarm here is set to 10 to the minus 6, and we have different spreading sequence length, 64. The size of the code is 60, spreading lengths of 128 and 256, and we can see that we can have probability, and we can determine theoretically the probability of misdetection. If we change the probability of false alarm, if we accept more false alarm, then we have better detection. If we didn't accept false alarm, then we have a lower detection. It's a trade-off. Okay, so in a glance, it's rapidly time, frequency, and phase synchronization. First, we are going to use the information given by the overmodulation to suppress the time ambiguity at the CCSK symbol level. So the overmodulation gives us a pattern of phase, and we are and if the pattern of phase that we observe is not coherent from the patterns of phase that we should observe, then we can say that we have a problem of synchronization at the symbol level, and then we can try other hypothesis. Then we can use the redundancy of the outer code to mitigate time ambiguity at the chip level by scanning the syndrome of the non-binary code and up to the point that it becomes high. We use the soft information given by the inner code and the redundancy of the outer code to estimate the residual frequency and phase ambiguity. And then we perform a coherent demodulation before the non-binary decoder. So just some ideas. If I have a payload of n equal 120 symbols, This is a theoretical lower bound given by finite block length regimes and given by work done by Valentin Savin. This is when we have a perfect synchronization channel. So that means the receiver knows exactly what is the frequency of the signal and when it arrives. And we lose 0.5 dB if we don't know that. So we have somehow the three links here that are the same strength, and we just are 1.5 dB from the channel limit. So just to show you that it works in practice, we did some offline experimentation. So we generate a file in MATLAB. Then we transmit it through GNU radio operators from two different rooms of my labs. Then we receive it, we put that the reception on the file, and we process it offline. So the frequency was the ISM band at 433 megahertz with a chip rate of 500 kilohertz. And here a bit useful bit throughput of 15 kilobits per second. We did what we call a CPR frame. That means the same frame repeated 61 times, and from one frame to the other, we just decrease the energy of the frame by 1 dB. So from here to here, there is 60 dB of difference. The payload is 120 bits. So at the end, this is the receive signal. So we can see here, this is the ground level, the noise level here. And we can see that we can recognize the shape of what we have received. And we have the first frame, the second frame, etc. So since the SNR is very good here, we can estimate it at 29.5 dB. We can estimate the frequency offset between emitter and receiver. It was 4 kilohertz. And here, absolutely no errors between the non-binary decoder because we have a very high SNRs. And then we can see in green all the frames that have been correctly decoded. And we can go inside the noise up to this point here where this frame has been decoded correctly. So it was minus 12.5 dB. So the channel limit is just here, more or less. Yeah. So it gives an idea of how far we can go with this algorithm. At the end, we had 35% of the symbols that were not decoded correctly. But since we have a non-binary decoder, it was able to recover the code word from this information. We did also some experimentation with a car in a mobile channel. So we put everything on a car, so a battery, a Raspberry Pi, a GPS, and a GNU radio board. We put the antenna on the rooftop of the car, so the emission antenna and the GPS receiver. We have a payload of 120 bits that contains the localization given by the GPS module, the Raspberry Pi temperatures, a frame number, and the time of the Raspberry Pi. So every 4 seconds, we send a new message. And at the receiver, we're on top roof of this building. And we have the board here, the new radio board. It is a board with a PC that has processed the data in real time and give us a success or failures of frame that we receive. So the emission was 4.5 dBm. It's quite low. LoRa, for example, is 14 dBm. The carrier frequency is still in the ISM band. So the bit throughput was here 3.9 kilobits per second, and the duration message 32 milliseconds. So we did a path in Lorient. So the antenna receiver were here, and we did a path. So we had some trouble at one point because we were crossing this road that is reserved for the people that live here. So we had a fine at this level. And okay, this is some results. So we can see that when we are near the receiver, the signal to noise ratio is very good. When we are far, for example, here 422 meters, we can see that we can recognize a shape, but it has been attenuated. And we can see that we are not alone. There is other signals that appear here. And when we are far away, we can't even know that there is a frame that is received because we are far below the noise level. But still, we were able to decode it in real time. We did also some experimentation with a company named Talos that wants to have some transfer data from buoy and a boat. So we put a buoy here that has been moving by the noise, by the wind from here to here. And then with the boat, we make a round trip around and making measurements. So we will do another proof of concept. We have some significant distance, so we will do another experimentation soon. Let's go toward multi-user detection. So let's say we did some, this is a preliminary first results on multi-user detection. So we set two orthogonal CCSK sequence called PN1, PN2, and we imagine a cell with a base station at the middle, and we have random devices spreaded randomly. And each time a device wants to send a message, it will select a frequency between Fmin and Fmax. So that means F0 plus or minus 12% of the bandwidth. We select randomly which sequence we are going to use. And so we have, for example, the first sequence, if I put it in red, then here with a high distance, here with a lower distance, etc. So this is frequency and this is time. At the receiver level, so this is the noise level. This is a superposition, a simulation of a superposition of all the frames that we received here. There is here 45 frames that have received simultaneously. And what we have is a summation on the noise and the frame. Okay, so this is the output of the detection match filters for the first iteration. So from the first PN sequence and the second PN sequence. So we have different color dots. So green means that we detect the frame and we decode it correctly. Red means that there were a frame here but not detected, and yellow either detected a frame or not a frame, or ghost, but not corrected. So we can see that at the beginning we had 8 decoded frames, and then for the second 6 decoding frames. So once we decode the frame, we can estimate its parameters, and then we can subtract it to the received signal. So this is called 6 receiver. 6 mean successive interference cancellation. So we have the level of noise at this point, the signals after the suppression of the first decoded frame, and then the superposition of the superposition of the signal. At the second iteration, we were able to decode 8 more frames from the first and 7 more frames for the second. So that means 99 frames among 45. And then at the fourth iteration, 43 frames were decoded and only 3 remain undecoded. So that means 93% of the decoding success. Okay, so let's go toward conclusion. What I would like you to remember from this presentation is that the QCSP frame, very low complexity at the emitter side, close to the theoretical limits. We did real tests in mobile channel and maritime channel, and also that we have a proof of concept for the unslotted aloha multi-user detection. We have a lot of potential application for LEO satellite, for example. We have a collaboration with a company on this topic. We have some contacts with water provider company that need to do remote metering. And we have also a maritime application with ongoing field experimentation. So we are working at the moment to improve the hardware-software implementation of the receiver, and to work also on the multi-user detection. So you can find all information on the project in this website. Thanks a lot for your attention.